Okay, so let's move on. Still, this is in section 4.1, and I would like to introduce one theorem and also one definition. Okay, and then we're gonna put all the pieces together to show you one example. Okay, and the problem says like this: the theorem, excuse me. The name is called the first derivative theorem for local extreme values. Okay, again, the local extreme means local maximum or local minimum. Okay, and it says like this: if the function f has a local maximum or minimum at a point C, this point is an interior point of its domain. Okay, and also the derivative of the function it is defined. Okay, at this point C. Then the theorem said that the derivative evaluated at this point C equals 0. Okay, so that's the first derivative theorem for the local extreme values. In other words, if you have a local maximum at a given point and the derivative is defined at that point, then derivative evaluated at that point 0. Okay, just repeat it. And okay, so with this theorem, and then now let's introduce one definition. A new concept is called the critical point. And it says like this: an interior point of a domain of a given function, f, where the derivative evaluated at this point is 0, or at this point the derivative is undefined, then this interior point is called a critical point of the function. Okay, of the function. So now let's see, guys. Let's try to think about here why we introduced this. We talked about the first derivative theorem for local max and local min, and then we introduced a critical point. Now, if we go back to the first graph we showed you, which is this graph. Now let's think about this question. Assume I have a function and on a closed interval, continuous, and I would like to know the absolute maximum and absolute minimum. Okay, and of course I don't give you the corresponding graph. How do we find the extreme values? So that's the main question here. And think about it. Right now we have this graph. You see that the absolute minimum happens on its left endpoint, right, in this graph. And the absolute maximum, it happens, do you see that this is one of the critical numbers, guys? Do you realize that? Because, and if we draw a tangent line across this point, do you see that the tangent line slope is 0? So correspondingly, f prime value at this point is 0. So what we can tell? Well, this tells us that, okay, to find the absolute max, absolute min, the candidates for being extreme values are critical points and the endpoints, right? So those are all the candidates. So with this in mind, so let me make a little bit summary here. Seriousness. Okay. So to find the extreme values of a given function, let's say fx, defined on the closed interval from a to b. Okay, this is a question here, and the answer, it goes to those steps. Step 1, find the critical point or points of fx. Step 1, okay. Step 2, and evaluate fx at the critical points and any points, okay? When we define the critical points as the interior point. At 3, compare and get the conclusion. Okay, so those are basically 3 steps. Now let's work on a example, a simple example to this. Let's see. Simple example. Let's do this one. So example 1. So given fx equals, let's see, 10x times 2 minus ln of x, and the interval is 1 to e squared, and the question is find the extreme values. Okay, in other words, absolute max, absolute min. So step 1, okay, step 1, see answer. Step 1, I take the derivative, right? Because that's to find the derivative is to find the critical point. Okay, so the derivative, you're gonna use the product rule, right? So it gives us is 10 times 2 minus ln of x, right? This is one of them. Derivative of this part plus 10x times the derivative of this, which is 0, right? Minus 1 over x. Okay, 1 over x. Our domain is from 1 to e squared, so we don't have to consider about, whether this part is defined or not. Well, in fact, when we have ln of x, we already know that the domain definitely going to be greater than 0, but it's from 1 to e squared. So that's the domain. And then this is what we have. We have 10 times 2 minus ln of x, right? Plus, for here, 10x times minus 1 over x actually give us this minus 10, right? And then you can do a little bit of simplification. We can factor 10 out, which is 2 minus ln of x minus 1. It gives us 10 times 1 minus ln of x, right? So you can tell, guys, on this interval here, from 1 to e squared, there's really no point can make my derivative undefined, right? Because f prime of x is this one is well defined on this interval here. So all we need to do is to figure out, okay, at which point the derivative equals 0, which is equivalent to solve for this, okay. And you see, set this part to be 0, this is 10 times 1 minus ln of x equals 0. You're going to see that basically this 10 is gone, right? Constant, so you're going to have this ln of x equals 1. And it's very easy to solve this x equals e, right? So this is the only critical point on my defined interval here. Okay, so the only critical point. Okay. Here. So that's the step 1. Step 2, let's see. evaluate, remember, evaluate fx as critical points and endpoints, okay? So let's do step 2 here. So normally, when I do the step 2, I would like to draw a table. So the first row, I list all the endpoint and then the critical numbers. So left endpoint is 1. I have critical number e, and right endpoint is e squared. Okay. And our f of x, I don't remember this. Okay, so 10x. So it's 10x times 2 minus 1 of n. Okay, 2 times 1 of x. And I started to do the evaluations here. So let's see. F of, f1, which is 10 times 1 times 2 minus ln of 1, right? Ln of 1 is 0, so we have, it's as far as 20. F of e is 10 times e times 2 minus ln of e, right? Ln of e is 1, so it gives us is 10 times e times 2 minus 1, which is 1, which is 10e, okay? So we have 20 here, we have 10e here, and f e squared, which is 10 times e squared times 2 minus ln of e squared, right? And if you remember one of the properties about the logarithmic and ln of e squared, actually this part is going to be 2. So 2 minus 2, this part is going to be 0, okay? And e, which is a natural number, or approximately about 2.718. Okay, so definitely this is going to be the largest number, right? This is going to be the smallest number. So our conclusion is, fx attains its absolute max at x equals e, and absolute mean at x equals e squared. Okay, so so we complete the problem here. Okay, so I'll stop here and then I'll see you again.